Hello! In this video, we're going to continue our discussion of the use of finite sums of areas of rectangles to approximate the area under a curve, then take the limit of that sum. And to do so, we'll make use of sigma notation or summation notation. In the previous video, we considered how to use the areas of a small number of rectangles to approximate the area under a curve. In this particular video, we're going to consider what happens when we let the number of rectangles whose area approximate the area under a curve go to infinity. We're going to first find the sum of a finite number of rectangles, usually involving something like n rectangles, and then take the limit of the sum as the number of rectangles goes to infinity. Let's take a look at this particular function, f of x equals 2x squared plus x. We're going to find the area bounded by that function, the x-axis, and the line x equals 2. First of all, we're going to partition the interval from 0 to 2, and we're going to use n rectangles of equal width with the right endpoint rule. And as you recall, the right endpoint rule says that once we make the subdivisions of the interval from 0 to 2, we'll use the right endpoint of each subinterval, plug that into the function, and that will give us the height for our individual rectangles. So if we use n rectangles of equal width, what's going to be the width of each rectangle? Well, we're going to take the width of that entire interval from 0 to 2, and we're going to divide that by n, and so we'll get 2 over n. When we now look at the partition for the interval, we're going to see that as we always say, the left and right endpoints of the interval, 0 and 2, become the very first, so x sub 0, and the very last, x sub n, terms of our partition. And then beyond that, if I make notes or make marks here, each interval would have to be of length 2 over n. So this right here would be 2 over n. If this width is also 2 over n, this is going to be at the mark 4 over n. If we have a width of another subinterval of 2 over n, then this is going to be the mark 6 over n, and so on. And we're going to continue. So therefore, our partition will be the points 0, 2 over n, 4 over n, 6 over n, and then stop when x is equal to 2. Now, it's going to be helpful many times when we're looking at working with these types of sums to note the pattern involved. And we can see that we're always increasing by 2 over n. But furthermore, I can say that it's 0, 1 times 2 over n, 2 times 2 over n, 3 times 2 over n, and so on. And even seeing that 2 is n times 2 over n, which makes the norm of our partition equal to 2 over n. As you recall, the norm of the partition is the width of the widest subinterval. And since all the subintervals are 2 over n in width, we've got our norm. Now, the sample points, as you recall, are the points that we use to find the heights. The sample points are the x values that we use to find the height of each rectangle. So, we said that we'd be making use of the right endpoints of each subinterval. So our first rectangle will be involving the sample point 2 over n. And so we're going to plug that into our function, and that's going to give us the height of our first rectangle. Our next one is going to be 4 over n, or 2 times 2 over n. And when we evaluate the function at 4 times 2 over n, that's going to give us the height of our next one, and so on. So our sample points are 2 over n, 4 over n, which again we can write as 2 times 2 over n, 6 over n, which is 3 times 2 over n. The kth sample point then will be, well, if we see the pattern, when we're on the first one, we're just taking one set of 2 over n. Sample point 2 is 2 times 2 over n. Sample point 3 is 3 times 2 over n. So it makes sense that our kth sample point will be k times 2 over n. Now, you may think that this seems silly because it's obvious. Well, it's not always going to be obvious. So it helps to write down what the sample points are and to write it in such a way that you see that pattern. Okay, and it is fairly easy in this case because our left endpoint of the entire interval is 0, and we're using the right endpoint. And those two combinations with the fact that we've got an increasing function will make this a little more straightforward than some of the other problems that you might be asked to do. Okay. If we continue on, our n minus first sample point, again the pattern continues as n minus 1 times 2 over n, and our nth sample point is 2. Knowing that the area of the region is going to be approximated by the sum of the areas of those n rectangles, let's look at the areas of a few rectangles and again look for that pattern. So the area of the first rectangle is going to be the first height times the first width. And the first height we said is going to be determined by the function evaluated at our sample point. So our sample point, our first sample point is 2 over n. We're using the function f of x equals 2x squared plus x. So we're plugging in 2 over n for each x value. And when we do that, we get 2 times 2 over n squared plus 2 over n, and then times 2 over n. And this was the width of our subinterval. Looking at the second rectangle, its area is determined by the second height times the second width. Again, our width is going to be 2 over n, which we denote using delta x sub 2. The height is going to be determined by taking our second sample point, c sub 2, which we said was 4 over n, and plugging that into our function f of x equals 2x squared plus x. But again, 4 over n we can rewrite as 2 times 2 over n. So we're plugging in 2 times 2 over n into our function. We get 2 times 2 times 2 over n, quantity squared, plus 2 times 2 over n. And again, that quantity, this all determines the height, and 2 over n is the width. And there we get the area of our second rectangle. Now, yes, we could multiply this all through and get maybe a little bit more compact formula, but that's not my goal here. My goal is to develop a pattern, and so it's going to be helpful to keep it in this format. Sometimes it helps to do a couple more. We'll look at the third case. The third area, or the area of the third rectangle, is going to be the third height times the third width. And again, it's going to be the sample point plugged into our function. So we're going to plug 6 over n into our function, or 3 times 2 over n into our function, multiply by our width, which is 2 over n, and we're going to see 2 times 3 times 2 over n, quantity squared, times 2. So this is 2 times x squared plus x times our width. Okay. And we see enough of a pattern so that the area of the kth rectangle is the kth height times the kth width. Again, the width is always going to be the same, in this case 2 over n. And when we plug in our kth sample point, which is k times 2 over n, into our function, I'm going to square that, multiply by 2, and then add k times 2 over n, and again, multiply that times our width. And when we put these pieces together, we find that the area of the region that we've mentioned, the area under the curve f of x equals 2x squared plus x, on the region from 0 to 2, is approximated by the sum of those areas of the n rectangles. And so if I write out again what we saw before, each of these, just in notation, expresses the height times the width. So this is the first times the first width, plus the second height times the second width, the kth height and kth width, and so on. Okay. And again, making substitutions, doing so to express the patterns that we're seeing. Each sample point, c sub k, is k times 2 over n, where 2 over n is the width of the subinterval. And I plug that into my function, I get this expression. But again, this expression shows the patterns. I've got the function evaluated at our sample point times the width. Okay, and there's the second rectangle, the third rectangle, our kth rectangle, and then our nth rectangle. The area of that nth rectangle. Now, it gets rather cumbersome to write this all out. But when we see a nice pattern and we see that the area of the kth rectangle always looks basically the same format, I can use summation notation to express the sum. And we noted that the sum of the areas of the rectangles look like this from the previous slide, which we can express as the sum from k equals 1 to n of f evaluated at c sub k times delta x sub k. And what that simply means is that for each term here, we see that it takes the same format. We're evaluating the function at our sample point, and we're taking it times our width. And we're seeing that our subscripts indicate which rectangle we're on. Our subscripts start at 1, meaning our first rectangle, and they end with our nth rectangle. So this tells us where k starts, where we end, and the form for the terms that we're adding. So when we see this form, and again seeing that this corresponds to f of c1 delta x sub 1, the area of our kth rectangle is expressed by this term. Each of them have that same format. I'm evaluating the function at k times 2 over n. I square it, multiply by 2, and then I add k times 2 over n, and then multiply by the width. So when I see that pattern, I can rewrite this sum more explicitly as the sum from k equals 1 to n of 2 times k times 2 over n squared plus k times 2 over n times 2 over n. And this looks like a little bit neater package, a little bit more closed form. Now, once we have a sum, we can act on those sums much like we would with our formula. Just once we have a sum like that, we can work with our properties of addition, properties of multiplication, and simplify that expression. But we also make use of some very standard forms of summation. And two of the basic summation formulas that we use are the sum of k going from 1 to n, and that's simply showing that we're going to add 1 plus 2 plus 3 plus so on, stopping at n. So we start at 1, we stop at end, and we're increasing k by 1 each time. And when we do that, we get the formula n times n plus 1 over 2. And you can look up, there are several different ways you can prove this and remember this. But for our purposes, we're primarily going to be using these two formulas. If we want to sum k squared, k going from 1 to n, that first looks like 1 squared plus 2 squared plus 3 squared. Again, we're stopping at n squared. And when we have that, our formula, that sum, can be expressed just as a formula in terms of n. Another example using one of these formulas is, suppose I want to sum 7k, as k goes from 1 to 9. If I write out the first terms of that, it's going to be 7 times 1 plus 7 times 2 plus 7 times 3, and continue until I get 7 times 9. And seeing that I've got a factor of 7 in each of those, I can really pull that 7 out in front, which is just 7 times the sum of k going from 1 to n. And at this point, I can use my formula that the summation of k things, the summation of k going from 1 to n of n times n plus 1 over 2 is just simply 45. So I get 7 times 45, which is 315. So we're going to use these two formulas to finish our work with the problem. of finding the area of the region bounded by 2x squared plus x on the interval from 0 to 2. So returning to this problem, again, I can see that I've got a factor of 2 over n, and since this factor does not depend at all on k, it doesn't change when k changes, I can pull that out in front. It's basically, it's a form of using the distributive property, and I'm factoring that out. Furthermore, I've got a sum of these items, 2 times k times 2 over n squared plus k times 2 over n. So I'm going to break that up and I'm going to write that as two different sums. So I've got the sum, I've got this sum and this sum, and both of those get multiplied by 2 over n, which I again can distribute that 2 over n across each of those terms. And now as I look at each of these expressions, again I see that this expression has a factor of 2 over n. Again, that doesn't change when k changes, so I'm going to pull that out in front. This expression, I've got 2 times k times 2 over n squared. I'm going to use my properties of powers, and I'm going to square each of those terms inside parentheses. And then I've got 2 and 2 over n quantity squared, neither of which depend on k, and so I can pull those out in front. And I've got 2 times 2 over n quantity cubed times the sum of k squared, k going from 1 to n, plus 2 over n squared times the sum of k going from 1 to n. And at this point, I see that I've got the same formula, got the same expressions as what we had when looking at the sum of k going from 1 to n, and the sum of k squared as k goes from 1 to n. So I'm going to make a substitution. And I've got a nice clean package where I've expressed the area of n rectangles, the sum of the areas of n rectangles. So it's an expression that only depends on n at this point. And I can simplify that a little bit. For example, I can simplify that a little bit. So for example, I can see that I've got a factor of 2 here, a factor of 6, leaving 3 here. I've got an n here, which can cancel with one of the n's in the denominator here. And I've got a factor of 2 and a 2 and an n and an n. So cleaning things up a bit, I get 8 over n squared times n plus 1 times 2n plus 1 all over 3 plus 2 over n times n plus 1. So again, this is just the expression for the sum of the areas of n rectangles used to approximate the area of the region bounded by f of x equals 2x squared plus x on the interval from 0 to 2. So if I wanted to say, well, what would the approximate area be if I used 100 rectangles? Well, I plug in 100 in for n, and I get 7.4336. Now, once we do this, if I want to calculate the exact area, I can take the limit of that expression that we just found as n goes to infinity. So I can take the limit, and I see I've made a mistake here. This should be as n goes to infinity of 8 over n squared times n plus 1 times 2n plus 1 all over 3 plus 2 over n times n plus 1. And in this first expression, we see that the highest power of n is 2. The highest power of n here is 1. So taking the limit as n goes to infinity, this is going to go to 2. This is going to go to 2. And so the exact area of the region bounded by f of x equals 2x squared plus x, the x-axis and the line x equals 2, we get 8/3 plus 2, or 7.3 repeating. Suppose instead we had used the left endpoints of the subintervals to give the height of each rectangle, and we can see that pictured here. What if we'd used the same number of rectangles, n rectangles of equal width? Again, each rectangle would be 2 over n units wide. Therefore, we'll have the same partition. So let's consider how things would be different if we use the left endpoints rather than right endpoints. Now, we can go through all the work that we just went through and identify what our c sub k's are, our functions evaluated those c sub k's, and so on. Or we can think more strategically and consider the work that we've just completed and say, how could I use that same information I just had and compare the region I have using the left endpoints with the region I have using the right endpoints. And for example, I see that this rectangle, the last rectangle using the left endpoint, has a height determined by -1 times 2 over n. So that's our c sub n. But the area of that rectangle is simply the area of this rectangle. And the area of the previous rectangle, this rectangle right here, is the area of the rectangle that would come just previously to that. So therefore, the two approximations differ only by the area of that last rectangle using the right endpoints. So I can take all the work that I just completed, look at the sum of using from the right endpoints and subtract the area of the nth rectangle using the right endpoint, which I know that area was based on the height of that rectangle and the width of 2 over n, but the height was 2. So this gives the area of that last rectangle using the right endpoint. I've got the formula based on n from before. If I now take the limit as n goes to infinity, it makes sense that this area of that nth rectangle will go to 0 because it gets narrower and narrower. So I get the exact same limit as I did before.